Good afternoon, all. Uh, I'm Deepak Kumar. Today I'll give my talk on the pendulum system, how we can see the any physical system, and how we can solve any physical system analytically and also numerically. So the topics today I'm going to cover are overview of the lecture, the motion of a single pendulum system. So this is the system I'm going to refer as my reference system. Uh, the methods I'm going to use for this lecture and the contents I'll be using, those methods and those tools you can use for any other dynamical system. So this is, you can assume that this is the reference model. And for this model, I'm going to use different techniques, how we can model physical system, how we can look their behavior over time, and how the system propagates over time, and how we can find state space model. So a lot of stuff we are going to cover in this lecture. So this is my first topic I'm going to cover. And second topic, the state space representation of the system. Even the system is linear, non-linear, it does not matter. We can represent any dynamical system in state space representation. Then we'll look MATLAB simulation for this pendulum system, how we can numerically solve this system in MATLAB, and we'll see the response over time. Then fourth part, we are going to discuss finding the fixed point or equilibrium point. So fixed point, generally mathematics people, they use the term fixed point, but if you are control guy, you generally use equilibrium point. That what is does mean, I'll also explain this part. Then based on the fixed point or equilibrium point, I'll linearize my system about that point. So linearization about the fixed point. And sixth part I'll cover. Once you have the linearized model about what I'll be getting about the fixed point, and based on the linear model, I can answer whether my system is stable or unstable. So from that system I'll be getting from this part. Basically, I'll find eigenvalues from that system, and based on the eigenvalues, we can comment whether my system is stable or unstable. So system stability based on eigenvalues. And seventh part, uh, then as pendulum system, if I hope you have gone through this system before, generally basically we have that is the length, and we have off here. So it can go this direction, it can this direction, also it can go vertically up. So what are the different conditions for vertically up, vertical down? So based on that eigenvalues we can discuss. So from this, it is basically condition for vertical up and vertical down. Okay. So then, based on the eigenvalues, also we'll look the vector field H portrait basically, how the slope changes with time, because here we are going to consider one is theta and another is the angular rate that I'll explain, and how we can find the phase portrait of the system. Then based on that, we also can comment about the system stability also from the phase portrait also we can say whether it is converging or diverging also you can comment. These are very important topic for analyzing the dynamical system, the phase portrait of the linear model. Then last part I'll be covering. The most important part is when the my system is when the my bob is here, even if you put some more small disturbance this side or that side, we can't able to maintain the position of this pendulum that upright position. So, so it means how we can use control to make this platform vertically up. So also we'll be giving some control aspect of using PID control. So control of the pendulum using PID control. So all this stuff I'll explain theoretical aspect also I'll show, and on the top of that also I'll be showing MATLAB simulation. So let me use different color. Yeah. So if you use Newton's second law of motion, we can find the. I'm not going to describe how the equation of motion of the pendulum system came, but let me write the equation of the pendulum system using Newton's law. So using Newton's law, second law of motion, the equation of motion of single pendulum system, we can write as theta double dot plus mg ml sin theta plus d by ml theta equal to 0. So here basically I can cancel this part. So right theta double dot g by, let me write the first derivative this side, d by ml theta dot plus g by l sin theta equal to 0. So I guess you guys very much, I mean, if you gone through the dynamics of the pendulum system, most of times you have not noticed this term in practice. Most of time you have noticed theta double plus g by l sin theta equal to 0. This is the very well-known equation. Most of guys you know this equation. But this term actually I have introduced because of the damping. If you have the drag force in the system, then generally we introduce this term. Okay, and how this term affects in our system propagation, we'll look that part also through simulation. Now, I'll write the state space representation. Of equation. Let's write this is the equation number 1 of equation 1. So that is actually, if you see this equation, actually this is the second order system. The highest derivative of the theta is double, right? So it is second order system. So I can write two first order differential equation. So if I denote x1 equal to theta and x2 equal to theta dot, and from this I can write x1 dot equal to theta dot or x2. Also I can write x1 double dot or theta double dot or x2 is x2 dot equal to, I can write minus k theta dot minus r sine. Okay, what is the r and sine? So I have reduced this equation in this form, some suitable form, theta dot plus k theta dot plus r sine theta equal to 0, where k equal to minus b by ml. ml b is the your damping coefficient, L is the length of the pendulum, and N is the mass of the pendulum, and R equal to G by L. So this is the gravity constant, and this is L is the length. So now, so we have this form. This is basically state space form. State space form, right? And let's denote this is equation number 2. Now, so we have two first order system. Now I want to see the response of this system, how this x1 and x2, x1 and x2, how they propagate, how they evolve over time. We'll see in MATLAB. So I'll switch off my system. Okay, I'll go to different system. I hope you can see my screen. I think it is visible.
Yeah, it is visible.
Yeah. Okay. I'll write the code for this state space. I'll write from beginning. CLC, clear my screen. I'll also clear all. And I'll find the system parameters. And here I'll assume my mass is 0.0.3. The damping coefficient I'll assume 0.05, and G, you know, G equal to 9.81. Okay, and also I have to L equal to 0.5. Okay, now for simplification, what I have done in my write up, I will also explain the same thing here and write the same thing here. So here R equal to alternate denoted by G by L capital N, and K equal to B by N cos L. Okay. And the pendulum system, what I have written in the paper, the pendulum system is F, let me write F equal to is the time, x is actually I have two parameter x1, x2, so x is a vector here, and I have x1 equal to x2, and this 2 minus k into x2 minus r sine of x1. Okay. So this is my system, and I will also give some initial condition. Initial conditions are int equal to, I have two initial. One is pi by 2.
Excuse me, sir.
How pi by 2? Yes, yes.
Sir, your volume is very low. Please adjust your mic, sir.
A moment. Is it clear now? Is it clear now?
Yes, sir. Yes, sir.
Oh, oh, oh. Rick, I can hear my voice. I can hear my voice.
Okay. I am. Which one? I have muted you from one of them.
Okay, fine. Now it is clear.
Okay.
That is fine. Sorry, guys. It was muted from my side. Yeah. So pi by 2 and 0. So why I am taking initial condition pi by 2 and 0, that I will explain later. So let me now consider the initial condition like this. Now I will solve the order. So here I'll use OD45. So I have time and I have instant vector x and equal to OD45, and I'll use f. I will put initial condition 0 to initial time 0 to, I want to see my response 0 to 10 seconds, and I have initial condition. I will take. Okay. So again I will plot the service. Yes. So plot. First I will plot it.
Sir, you are not audible to us, sir.
Yeah, it is not audible.
I can hear you. Is it not audible to some of you?
Yes, sir. Yes, sir. Now it is
It's audible, sir.
Okay.
Okay, fine. So it is. That is audible, right? That is audible, right?
Yeah.
The problem again, I can hear my voice.
No. Actually, I muted you in one of them. So the one I muted you was the higher volume one. So I just switched it.
Okay, fine.
Now you are audible properly, I think. Yeah.
Audible, but I can hear myself.
No.
Yes, I can.
Can you?
Yes, it's still I can hear.
Oh, it's getting reflected from my side.
Yes. Okay, no problem. So plot. No, Eric, it is disturbing. Please do something.
Yeah, I have muted everyone. So I have given you the permission for a co-host, so you can also mute anybody you want.
Okay. Still I can hear. This is time, and this is amplitude. So let me plot this. Rick, hello?
Yeah.
Rick, it is really disturbing.
But I am unable to find who is from where it is coming, because all of them are. I can see that everyone is muted except you.
Hello?
Hello?
Yes, hello?
Yeah.
Still I can hear. Maybe the problem I'm using two systems, that's really the.
Okay, I have muted you on this one. Please unmute yourself on the other one. I think the other one was better. Can you hear me? Yeah, please unmute yourself on the one. I have asked you to unmute.
Hello?
Yeah. Oh no, not this one. The other one. Hello? Yeah. Yeah. Now I think this is better.
This is, I think also it is better for me.
Yeah.
Okay, let me see the response of the system. Okay, this is the response we are getting, and you can see that uh, the blue one actually, that is actually the theta, and the larger overshooting was the theta dot. So here, time progresses, the system anyway is going to stable after some time. If you increase the time limit, like if you increase the time limit, hundred seconds. So this is basically the response we are getting, and you can see that as time progresses, the system is going to zero. The theta is going to zero. So if theta is zero means it is actually our initial condition is pi by 2, right? Theta x equal to pi by 2. So in this case, my system is anyways vertically up, but the problem is we have lots of overshoots. We have, I mean, if you see that till 40 seconds, we have lots of overshoots. The system is taking too much time to stabilize. Now, what I'll do, if I remove this damping, so what will affect? We'll see. Let me just I put b equal to 0, and I'll simulate again my result. You see, this is the problem. This is not stabilized at all. We have lots of overshooting. Can you see my plot, guys?
Yeah, I can see your plot, but I have a suggestion. Can you dock this plot into your MATLAB windows? Then you do not have to switch again and again.
Okay.
On the right hand side, that arrow, upper right hand side, the arrow in the plot. Upper, yeah, that arrow. Yeah, and then you can share your MATLAB.
Yeah, this is right.
Yeah, this is better.
Wow, nice. So you can see that even we don't have damping in the system, we can see there's a huge oscillation. So that's why damping is very important system. If you see the mass spring damper system, because of damper in the mass spring damper system, the system as time progresses, the system decaying, actually exponentially is decaying. But in this case, if damping, there is no damping, your pendulum system will not destabilize any of the coin. What we have considered our and time progresses, it is a key possibility. So now this is what we have seen from the numerical simulation. Now we'll look how our system can behave at the defined equilibrium point. So for that, we need to go some basic how we can use linearization technique, how we can apply linearization methods. So I'll switch to my defined system. Again, we'll come back to here for the control part. Yeah. So this screen is visible, Rick.
Yeah, yeah.
Yes.
The screen is visible.
So now the equation we have written here, x1 dot equal to x2 and x2 dot equal to minus k dot r sine theta, or I can write minus k x2 r sine x1, right? Because our x1 is theta and x2 dot theta dot equal to x2. So now what we'll do is we'll linearize our system about some fixed point. From this equation, we can write, if you see the fixed point, how to find fixed point, how to find fixed point. So we have pendulum system and we'll find the fixed point for our pendulum system. So here, this is basically also equal equilibrium point. When if we suppose we have system x dot equal to f of xt, when this function when we make to 0, and basically what we are doing when the system does not exhibit any external potential and the system has initial tendency to return to that point. That point actually we call fixed point or equilibrium point. Now this equation also we can write x dot equal to f of x. So if we can make this part and this part to 0, we can find the value of x2 and x1, and those points actually we can call fixed points. Now let me write how can we find these points. So if I put for x2 equal to 0, this is only one equilibrium point, and for x2, now if you put this part equal to 0 minus k x2 minus r sine x1 equal to 0, and if you substitute x2 from the 0, we'll have minus r sine of x1 equal to 0. So we'll have for x, we have two equilibrium point, one is 0 and another pi by 2. So this is actually two equilibrium point. Sorry, it is not pi by 2, it's pi actually, right? So 180 degrees is going up. When the pendulum is vertically up and down, it is 0, and it is going this here, it is actually pi. So I can define my equilibrium point, two equilibrium point xc1, I can write it 0, 0, and another equilibrium point is 0 and pi. So this is two equilibrium point way. Now, so once we find the equilibrium point, we will linearize our system about that equilibrium point. So what is linearization actually? Let's consider this is my equilibrium and I have some region of about that equilibrium point. So I'll consider some small small distance delta x. So this is my equilibrium point. Let's consider this is the x1 or xc2. So about this equilibrium point, I'll find some region which is distant by delta x, and I'll see my system. This system, what the system, this system basically will behave as a linear system. That is actually called linearization process. So here basically we use scalar series to find the linear system. So how we can do is, I'm not going to discuss what is scalar series. So what I'll do, I'll write something, the delta x from X, the region at which the system look like a linear system. And the system can be written as linear form as x dot equal to x. So this is very, if you have done some linear course, or if you see this kind of system, basically x dot equal to x, because a is the constant matrix for our case. So this is basically linear system. Also it can be time varying. In that case, system will be time varying system. So LTG. So now the thing is, in this case, this is basically linear system. But the system we considered before, this is basically nonlinear system because of this sine term. So now the system we have, now it is, there is no sin x term, it will be linearized about this some point. So how to do that? So here A actually our Jacobian matrix X, which is linearized about one of the equilibrium point. So if you this is in our equation, right, because we have two into matrix, because we have two states, right? So this A will be 2 into 2. So now this Jacobian matrix OF X equal to, I can write dx1 by dx2, df1, dx2, df2, dx1, df1. So this is basically Jacobian matrix. Now we'll apply this part in this equation. So we have, this is basically our, so x1, x dot equal to x2. This is, let's consider this is the f of x1. Let's consider, even there is no x2, let's consider this is f of x1, x2. And I have another system. This is also, we can write, this is f1, f2, x1, and x2, which is actually basically minus a x2 minus r sine x1. So I have denoted these two systems as f1. Now apply this linearization technique here. So after linearizing, we can get tau x dot equal to dx dx dot dx. So this is basically the system which is in this area. Actually, what I said in this area. So if you see, our rho x is the parameter, the state. Now this complete system is reduced to this form. This is, if we apply Taylor series, we can find. So I'm not going to use how to find. Just this is basically linear system, which is can be linearized about one of the point. Now, also this part we can write x of x. So from this equation, let's write this equation. So from equation 4, we can comment what kind of system is. Whether it's stable or unstable. This conclusion can be given by the based on the arguments. So now So if I apply this equation for the system, for this system, you have right 0, 1 minus cos x1, then try by yourself minus k. Now we'll consider the first equilibrium point x0.
Hi Deepak,
Yes.
your voice is getting low sometimes. So
Now it is clear?
yeah, now it's clear. I think yeah, you are getting away from the mic sometimes while writing.
Okay.
So, yeah.
Okay.
I got that in the comment section also. Okay, thanks. Yeah.
I'm not able to see my comments. No, okay, I'll correct. So this is xc1. I'll consider the first equilibrium point, which is 0, 0. So about this 0, 0, we'll find this matrix. So it is 0, 0. So now at this point, we can our A matrix, we can write 0, 1, minus 1, and minus k. So this is the condition when if you see 0, 0 is the equilibrium point where my pendulum is actually vertically down. This is actually 0, 0 equilibrium point. This is 0, pi and 0. So I have two equilibrium point. So about this equilibrium point, around this delta x, this is the region where my system is look like linear system, and the linear system which is can be given by x dot equal to a x, and this is, let's denote, this is the a which is actually down. So here. Okay. And now we'll find our second, system at second equilibrium point. So at the second equilibrium point, the equilibrium point is pi and 0. And the A matrix is 0, 1, 1, and minus k. If you substitute the pi and 0 in this system, in this equation, our A matrix is reduced to this form. Now, if I write the system about the vertical up position, I can write A of x. So this is the system for down direction. This is the system for up direction.
Excuse me, sir.
Yes.
Sir, it is not audible actually.
I don't know what is happening. Just a moment.
Okay, hi Deepak. I have asked you to unmute yourself in the second one. I think when you are doing something in this one, then the second one will work better, probably.
Okay, it is better if I don't use my headphones.
Because yeah, sometimes the voice is getting very low.
Okay, just a moment. I'll stop my headphone. I think because of that, maybe you are facing this. Now it is okay?
Yeah, now it's okay. It's very loud now. Yeah, thanks. Yeah.
It's better now, right?
Yeah, much better. I think, yeah, it was a mic problem, something like that.
Sorry. So now I hope it is clear now.
Yeah,
Okay.
Yes, sir.
Yes.
We have missed. I hope. Okay.
So can you please quickly go through the two lines that you have written? I think from there the mic problem started. So that will be.
Okay, where you have faced the problem, can you tell?
Yeah, df dx equal to that, and then the two lines, and that will.
Okay. So basically, this is the equilibrium point. First equilibrium point. First equilibrium point. This is my system, and then the second equilibrium point we have this is the system. So this at this point, the system is given by this. At this point, my system is given by this. So because we have two equilibrium points, so at two equilibrium point, we'll have two region where we are basically this region we are defined by the Taylor series expansion, basically where we are using this unit. Okay, so this is the two system at vertically up and vertically down. Now we will look the eigenvalues at this of these matrices AD and AU. We can let me write something for both the matrices. We can find eigenvalues and comment on stability. Okay. So let's assume my k value is something 0.5. Let's consider k is 0.5. So now A D becomes 0, 1, minus 1 and minus 0.5, and AU becomes 0, 1, 1 minus 0.5. Okay, these are two matrices. So first let me write the eigenvalues for this matrix. So if you remember, the eigenvalues you can find from the determinant of characteristic equation, that is actually lambda I minus A equal to 0. So from this, if we solve this equation, my lambda 1 and lambda 2 are given by lambda 1 is and 2 something 0.05 plus minus I. So you can check it, maybe if I have chosen some values and MATLAB have run. I can't remember what value I have taken, but basically this will be some real part and an imaginary part. So you have noticed something, when you have negative real part and you have imaginary plus minus, doesn't matter this part, but if you have imaginary part and real part if it is negative, then we can have the response like this, because this is the function actually decaying. So if I write in, suppose xt is my system, xt is my theta, so I can solve xt equal to c1 e to the power minus 0.05 and it should not be c1, this is t, and c1 e to the power plus 0.988 I plus C2 e to the power minus 0.988 I. So this is kind of system. So if you see this part, this is basically oscillating. So it is actually continuous oscillation is there. But because of this part, if you see this plot, it is basically exponentially decreasing with time. If I look this part only, but due to this part, this oscillation actually decaying with time. Okay, so this is what we are seeing from the system when the vertically down. Now let's look the systems at vertically up position. So similarly, we can find at equilibrium point, xe2 equal to pi and 0. So we can write the eigenvalues equation delta lambda I a up equal to 0. So if I solve this equation, my lambda 1 is coming to be minus 0.50512, 1 lambda, and another eigenvalue is 0.95, sorry, 9512. So if you notice here, we have one eigenvalue which is positive, another eigenvalue which is negative. So this is very, very important things in on the stability. If you have system and if any of the eigenvalues comes out to be positive, then system is unstable. So in this case, system is unstable. Even the if you have thousands eigenvalues, doesn't matter. If any of the eigenvalues comes out to be positive, then system is negative, sorry, unstable. So in this case, system is actually stable because it is going to your equilibrium point, right? Even there is oscillation. Now we'll look some basic fundamental things how we uh, see the system in phase portrait, how the system behaves. Because here actually we are looking at the uh, how your xt is changing with time, right? Xt, how it is going with respect to time. So now we'll plot something x1 versus x2. Okay, so how the x1 going to change with respect to x2? Basically, this is basically how we can say different way dx2 dx1. So how your x2 going to change with respect to x1, small change in x2 with respect to small change in x1. So how the slope is going to change over time? This is what we are going to look. So now what to do? Let's consider if you remember the linear transformation, if you have system not in diagonal form, we can transform the system in diagonal form using linear transform. Okay, so before we move to that part, let me write something. So based on the nature of the eigenvalue of the system, we can analyze the state trajectory. Trajectory is basically the space portrait. So based on the nature of eigenvalues, the nature of the fixed point can be classified. So this classification, if you here actually based on the nature of the fixed point, so how my fixed point is, how, so what I have drawn there, if you remember, this is my vector field and I have considered some region of attraction or some region about this equilibrium point. So here, based on this eigenvalue, sorry, based on this fixed point, how my system will behave around this fixed point, I can see through the phase portrait trajectory. Okay, and based on that, I can classify the nature of the plot as node, focus, saddle point, and vortex or center. So based on the nature of the eigenvalues, we can define the phase portrait in different way. These are the different kind of, structure, the graphical representation of the slope. Now, if we apply the linear transformation, so the above system can be written as x dot equal to mz, right? So from this, I can write, if you apply the linear transformation, so z1, actually this is z, okay? This is z. Actually, if I transform z equal to some tx, so this is the way we transform the x domain to z domain. So z1 dot z2 dot I can write, this is, you can go some basic mathematical book, there you can find how we can linearize the linear, how we can apply the linear transformation to a OD system. Lambda 1 0 0 lambda 2. So this is basically Z1 and Z2. You notice in this system, the both the system actually decoupled. They are not dependent to each other. It's basically, if you have a diagonal eigenvalues, so I can write from this system Z1 dot equal to lambda 1 Z1 and Z2 dot equal to lambda 2 Z2. So I have two systems, system 1 and system 2. So I have two systems where they are decoupled to each other. Now, if I find the slope from these two systems, I can write dz2 dz1 equal to lambda 1 z2 lambda 2 and z1. And from this I can write dz2 z2 equal to lambda 2 lambda 1 dz1 and z1. So if I apply, if I solve for z1 with respect to z2, natural logarithm z2 equal to lambda 2 lambda 1 and natural logarithm of z1. So again, if I solve for z2 with respect to the function of z1, I can write z2 equal to c some constant, which is this constant, it z to the power z1 to the power lambda 1, sorry, this is not constant of this, so z1 and sorry lambda 1 lambda 2. So here c is the constant of integration. Now, based on the nature of the eigenvalues, these eigenvalues, we can conclude what kind of response you may get. I mean, phase portrait you may get. One is node, focus, saddle point, vertices. So now let me see how we can look. Now, case one, if the eigenvalues are real and negative. So in this case, we can get lambda 2, lambda 1 equal to some positive, it is constant 0. Now my response actually z2 equal to cz1 k, right? But please remember lambda 1, lambda 2 are negative eigenvalues. So in this case, the phase portrait look like, so if you look this system, if you look this two system, it is easily we can see that the equilibrium point is 0 0, right? So if we put this equal to 0, this equal to 0, so we'll have z1 equal to 0 and z2 equal to 0. So we have equilibrium point 0 0. So if you have equilibrium point 0 0, let's assume this is my equilibrium point. So we can now see the nature of the plot, I mean phase portrait around this equilibrium point. So the nature will be something like this. So it is actually converging to the equilibrium point. So this is my equilibrium point, fixed point, and it is actually called saddle point node. Sorry. This is a stable node. Okay, this is a stable node. Now, if we have any of the eigenvalues, now let's consider if both the eigenvalues, if the eigenvalues are real and positive. So in this case, we can write that is fine. You can write k greater than 0, but please remember the eigenvalues are real and positive. So in this case, we can write the response. This is my equilibrium point, Z1 equal to 0 and Z2 equal to 0. And this is similar plot I can get, but the direction will change. So it will be diverging. So the system, so it means the pendulum system, this is my equilibrium point. Let's connect to pendulum system. This is my equilibrium point vertically down. So even the eigenvalues at the vertically down position, the eigenvalues, the A matrix, AD, if the eigenvalues of the AD matrix are negative, we had minus something A plus IB, right? One real part was there and imaginary part was there, plus minus. So even if the eigenvalues are in this structure, in this form, if you have real eigenvalues, so the system will going to like this. But here actually this part is 0, it is more stable, right? Here actually I have considered real and negative, so it is more stable. But in our case we have eigenvalues IB form, that I'll come to later, maybe just after a few minutes. So this is actually, it means if your eigenvalues are positive, if the eigenvalues are positive, in this case your system is actually diverging. You can't able to stable. So for that case, you need to design your control, right? Now we'll consider another case. If the eigenvalues are real, one positive and one negative. So in this case, you will have, okay, this is actually called unstable node. So in this case, your nature of the plot will be something. This is actually like this. So this is actually, you'll have, this is my fixed point. So around the fixed point, the nature of the phase portrait looks like this. And if you have plot like this, it is called saddle point. Now we'll consider eigenvalues are complex. Case 2. Complex eigenvalues. This is very, very important because this is more suitable for our system, what we are considering pendulum system. So first case is, if the eigenvalues are complex, eigenvalues are complex with negative real part. So actually this is exactly we have in our for our pendulum system, minus A plus minus IB. This is the one we have for vertically down system, right? So in this case, the phase portrait will be looking like, you see, this is actually diverging to the equilibrium point, and this is called stable focus. So again, if you have eigenvalues are complex with positive real part, so plus A plus minus IB. So in this case, the response will look like, so it is basically diverging. So it is called unstable focus. Now another condition we look, see. So it means if you're, in our case, in pendulum case, even you disturb, If the system is linear and if you disrupt some part of to some perturbation, the system will automatically go to the equilibrium point. So even if it is vertically down, so if you put some if you apply some disturbance, maybe it will go to that position, but after some time it will go back to the initial point. Now I will look the system with the eigenvalues with zero real part. So eigenvalues with zero real part. So in this case, the phase portrait look like this is the orbits, closed orbits. Okay, one thing, these are the plots x1 with respect to x2. Sorry. One thing I have to say, all the plots here I am doing for phase portrait x1 with respect to x2. dx2 by dx1, how the slope changes. So if you have zero real part, so if you have something IV form, so you may have the response closed orbits. This is called closed orbit. This is more related to that limit cycle, or limit cycle is something different, but if you consider that our orbits is for space mission, these are the best example. Now we'll go to MATLAB again, how we can see the phase portrait for our system. So now I'll stop here. So let me share my screen in MATLAB. So here I'll go to open. Can you see my MATLAB command window?
Yeah, it's visible.
Yes. So here I'll see my response, the phase portrait. So can you see the PP plan?
Yeah. So everything is visible in the MATLAB.
Okay, very good. So PP plan also you can see, right?
Yeah, everything. Your entire MATLAB is
Very
inside.
good. Now, so here, because our system is different, I'll change this function. It is actually, we are having x of 2, right? So let's write x. So it is y basically, right? In our case. So here actually, I'll change minus, we have, let me see what I've written here. I forgot. Yeah, minus 0.505, we have considered k equal to something 0.5 and y minus sine of x1. So x1 is x here. So now let me plot this. It's not entered correctly. Okay. Yes. So here you can see very interesting things we are going to see. The phase point is it visible? Now it is visible, right?
Yeah, everything is visible.
Yes. So you can see this is the face portrait what you are getting actually. So this is how we are getting. You see, in our case, one is our stable equilibrium point, another is unstable equilibrium point. So one is the stable focus actually, right? This is what I have said, that minus A plus minus IB. So this is the equilibrium point in our case, and it is coming like this. This is the coming like this. This is the, and another one is the unstable saddle point, that is actually in the right hand side because of the graph margin we are not able to see. But in the vertical down, for the vertical down position, we can see that the phase portrait are going to your fixed point, equilibrium point. Even the system is disturbed with some perturbation about that region, the system automatically goes to the equilibrium point or fixed point. So now we'll do some MATLAB coding for this, the rest of things, how we can do. So here, let me go back to the coding part. So here, I'll see for the vertically up position, how the response look like. Okay. So let me comment it. Numerical solution of linear OD, the pendulum system. So this is, I will write my A matrix. So in this case, the A matrix is 0, 1. It is actually vertically up. Right. So here actually 0, 1 and 1 minus 0.5. So, and let me take the initial point is, now you can understand, if the vertically up position, the initial point is pi by 2. It is now clear why I have considered in the numerical analysis here, why I have considered the vertically. This is the point actually, pi by 2. So here I am considering the, for the vertically up pointing, for the vertically up position, the pendulum equilibrium point is pi by 2 and 0. Right. So now I'll take the same function here. And I'll solve it.
Hi, Deepak, you are not audible.
Yes, it is. Is audible?
Yeah, yeah.
Yeah. So now we consider here we have to change it because we have considered linear is the model basically, right? So it will be x2 and you have to consider minus 0.5. Okay, and so I will copy and paste, and I'll see the response. You see, when the vertically off, the response actually not, the system is not stable. But we'll be using some control how we're gonna do it. Maybe in the coding, I can't explain in my laptop because it is a big thing, but simple I'll use how to use PID control to stabilize this part. If you see this part, you see as time progresses, it is actually going away, because also if you see the eigenvalues of this response, if you see the eigenvalues, EIG equal to A, clear this part. So if you see, you can see, we see one positive and one negative. So it's a system is unstable, completely unstable. Now we'll look the system for vertically down direction. So we'll just copy and paste this part here. And actually for vertically down direction, our A matrix was -1, right? 0, 1 and -1. So in this case, here also we have considered minus, and so let me plot this. Yes. Oh no, it's not. Okay. Anyways, the eigenvalues is negative, but my system response is why not changing? So let me quit this part and plot again. Yeah, you see? Okay. Yes. You see, as even the vertical, this black is actually theta. So you can see that when there's a vertically down, after some time, the system is going to your equilibrium point 0, 0. It's near to 0, 0. But when it's vertically up, let me retest again this part. It is actually, you see, unstable. It's like black one is the your point. That the theta actually is going down actually. So now we'll use some control how we're gonna do it. This is the, I mean, even in the vertically up, vertical down position, if you apply some control, we can make the system stable. Now how to do that? So let us do some control. Control is everywhere. Without control, you can't do anything. Even some unstable system, we can, even there is unstable system, we can make it controllable. Okay, now what we'll do is we'll find our system transfer function first. So I'll only consider theta only, right? Theta, the only variable I need to see. I don't want to control theta dot. Theta is the main variable I need to concentrate. So design of PID controller. So we have A matrix A equal to. So let me consider first vertically up direction. Okay, vertically up direction. When the pendulum is vertically up. So A equal to 0, 1, minus 1. No, minus 1 is vertically down. 1 and minus 0.5. 0.5, right? 0.5 is fine. So now this is my A matrix, and let's consider B equal to, because I need to apply control. So control is the only force should be applied to dynamics. But if you look the structure of the system, and x2 dot equal to some function, nonlinear function. So that is actually dynamical equation, and we need to apply the control to that system only. So in our case, b vector will be 0 and 1. So here actually we are not looking the system as x dot equal to x. Instead of that, we are looking the system x dot equal to x plus bu. And we have the only state we want to measure is x1. So if you remember the state space representation, x dot equal to x plus bu, y equal to cx, and c is the actually number of the states you are looking to. You want to look at the output terminal basically. So 1 and 0. So I want to look basically c equal to your C matrix, the matrix into the vector x1 and x2, but I am not care about my x2 equal to 0. So here the system I get equal to SS space form A, B, C, and D. So let me solve this part. Yeah, this is my continuous time state space model. Okay, this is the state space model I got. Now I'll find the transfer function of this. So I'll find the transfer function means that how the output is x, and how the x is going to change with respect to u. U is the control. I'll define just a moment. I'll define now. So now the system transfer function TF, I can write SS, and I'll use PID control KP equal to 1. I'll consider KD equal to 1. Let me put all the gains of the control parameters, and gain parameters equal to 1 only, yeah? And KI equal to 1. This is very interesting things going to happen. Now the controller part I mentioned like CPID. So if you put the gains, so automatically you can find the PID controller. KI, KP, proportional, integral, first should come proportional derivative, and then integral, right? Okay. So this is my PID controller. If you want to see the structure, I can show you, but it is not having. So now PID is KP, KI, and KD. So let me see. Students, This is equal to 1, QD equal to 1, PI equal to 1. It should work. Sorry, it is actually, I have written it as capital, it's really small. Now still this problem. Okay, I have already file. Let me check where. Yes, it's working here. Okay, so here actually see, this is my transfer function. KP, KI, the same thing I'm doing there, but not able to. This is funny. Okay, so this is the contains and structure of the PID control. Let me check here. Yeah, this is the PID control. You see, this is the PID control, Kp in plus Ki into 1 upon S, Kd into S. If you write in time domain, Kp plus Ki integration of E dt plus Kd into E dot. So this is basically your PID control. And if I write in state space form, the equation becomes, including the pendulum system, the system become, let me check how the system look like. This is the system. So this is the transfer function, basically xt theta versus u. U is my PID control. This is the C basically. So x theta by C, this is my transfer function. So now I'll see the response here. Let me see the response. Yes, but this is not response, sorry. Yes. I'm going to share something interesting result. So this is, you see the result, fantastic result. So if you want to apply the PID, if you apply the PID control, you see the response after 26 seconds, it is just completely vertically down. Even the system is, if you put up to some disturbance, after some time, the system is going to 0. So theta is exactly 0. So this is the case we considered for vertically down condition, and our A matrix was 0, 1, -1, minus 0.05. Right. So this is the matrix we obtained for vertically down position. Now we'll consider about vertically up direction. We'll consider the same control parameters, Kp equal to 1, Kd equal to 1, Ki equal to 1. Now let's look the response. This is the response. Very bad response. You see, if you apply the control, if the pendulum is vertically up direction, you can't able to control the pendulum. After some time, it is going to fall down. So now with control, so it means I told you control can handle everything. So here actually what I have to do is, so I have to put more control effort. I have to apply more control signal so that my system can, my controller can able to make the pendulum vertically up. So what I just increase the gain. So increase the gain means I put more energy, I put more power. So let me check if I increase the gain. It is the vertical up position, but previously the response was very bad. So now let's see the result. Let me, yes, it's coming. Yes, you see, this is the response we are getting. It is going, but let me do some correction here again. Second. if I put, if I increase also some value of 30, but still the system is controlled actually. It is going stable actually. Let me put this figure on. Yes, now we get the response. Now I'll compare some result here. So first, let me, okay. You see response? If you increase the control gain, if you put more effort, your system is going to control, even if the vertically up position. So what you have learned from this, if the system is even unstable, so with the control you can make the stable. So in the vertically down position, so vertically down position for this case, if you see, first let me explain on this part, this figure. You see, in the vertically down position, we have lots of oscillation. We have huge oscillation throughout till we can say 20 seconds. If you see it, if you enlarge this figure, you see there's a huge oscillation till 15 seconds around. But if you see the vertically down position, in the pendulum vertically down position, there is less oscillation in the, let me see the figure first. This should not be vertically up, this is vertically down actually. This is the right. And this is the case vertically up. Okay. So if you see this figure here, if you see this figure here, vertically down, you can see, now let me this figure, yeah, you see there's a less oscillation. Number of oscillation is reduced, but the problem little bit is there, there is some overshoot still after 20 seconds also. But the good thing is the system is, even with less oscillation, is going to settle down at the equilibrium point 0, 0. But in the previous case, even the vertical position is, if the pendulum is vertically up, and if you disturb a little bit, it may go down. But if you use proper control, like KP, if you increase the proportional gain 100 times compared to your particularly down position, you can make the system stable. But only thing you need to have to put more effort. So this is what for the pendulum system, and this is my end of the lecture. Thank you very much.